Okay, so I'm going to walk through with you now the development of quantum mechanics. And we're going to go step by step, and I'll tell you, we're going to tell you some weird things, and hopefully it will be sort of at the right level of detail that will be useful to you in an introductory chemistry course. So first of all, particles and waves are not the same thing, right? We know that. Particles and waves are not the same thing. In the macroscopic realm, that's where we live, right? But by the 1920s, it became increasingly clear that when you get really small, a different set of rules predominate, okay? Now, this statement here says there's a different set of rules, and that's not entirely true. Everything follows the same rules. However, when things are big, where you and I live, that set of rules called quantum mechanics are negligible, and they just disappear into the background because they're so small, okay? But when you get small objects, then all of a sudden those rules for physics become important, non-negligible. In other words, we can say waves and particles are not the same thing in a big world, but in a small world, we can't. I know. I warned you, this is going to be weird, okay? So let's talk about waves for a second. Suppose you've got some little puddle right here, and drops are falling into there. Can you see you got a drop, boom, sort of simultaneous drops? Well, when these waves hit each other, they undergo something called interference. And you get constructive interference where the waves get bigger and destructive interference where the waves get smaller. Right? Can you see how this wave comes out and you get these circle waves here? Wave fronts, right? And these wave fronts come out, and when they hit each other, weird things happen. Right? And it's called interference. It's called interference. I say weird. That's not so weird. You've seen stuff like that before, but it's a little difficult to predict. But it's called interference. All right? Now, Louis de Broglie said if electromagnetic radiation can have particle-like character, can electrons and other submicroscopic particles exhibit wave-like character? What? In other words, if light can act like particles, can particles act like waves? Of course. What a good question. So in 1925, Louis de Broglie, in his PhD thesis, he was a graduate student, extended the wave-particle duality of light that Einstein used to resolve the photoelectric effect. Okay, 1925, Louis de Broglie, probably pronounced correctly, Louis de Broglie is my guess. Okay, so he gave us the de Broglie wavelength, which looks like this. The de Broglie wavelength is equal to h over mv. This is a v now, no longer nu. Or h over p if momentum is equal to mass times velocity. These are the same equation, right? So this is the de Broglie wavelength, and it goes like this. This is Planck's constant. This is just a number. H is equal to, well, that's going to be a little bit ugly, is equal to 6.626 times 10 to the minus 34. We just looked it up, right? Joules seconds, I think. I forget what the units are. It's not minus, it's 6.626 times 10 negative 34. So it's just a number we look up, right? That's just a constant. And then we take the mass of the particle and the velocity of the particle, and we can get the wavelength of the particle. Yes, the wavelength of the particle. Okay? So Bohr had postulated that the electron, as being a particle, orbits the nucleus in quantized orbits. De Broglie argued that Bohr's assumption of quantization can be explained if you consider a circular standing wave. Like a standing wave is like what you might see in a guitar string. Only an integer number of wavelengths can fit exactly within the orbit. Okay, so here's a picture of this. Suppose this is your orbit. And yeah, you can see that if this is the wavelength from here to here, you got 1, 2, 3, 4, 5, 6 waves. But you can't put 6.5 wavelengths in here if it's a standing wave, right? Or 6.11. You can't do that, right? You can put 6 waves in there, you can put 7 waves in there, you can put 5 waves in there, but you can't put 6.11. So in other words, it's quantized. All right, so for a circular orbit of radius r, the circumference is 2 pi r, right? That's just what we get from geometry. For a circular orbit of radius r, the circumference is 2 pi r. So de Broglie's condition is blank. 2 pi r is equal to n lambda, where n is equal to 1, 2, 3. Since the de Broglie expression relates the wavelength to momentum and hence velocity, this implies the following. Okay? So we're not going to get too deep into this, but let's look at this now. The classic angular momentum, L, for a circular motion is such and such, right? Radius times the momentum for a circular orbit. This expression can be rearranged to give Bohr's formula, where am I here? To give Bohr's formula for the angular momentum. So the angular momentum of an electron is given as this. N times Planck's constant, or the h bar, which is h over 2 pi. Okay? This diagram shows the angular momentum for circular motion. I don't want to get into this. The angular momentum is actually perpendicular. You see how angular momentum goes there? It's actually perpendicular to the mass and the velocity. By the way, this is why bicycle wheels work. Yes, this is why bicycle wheels work. When I was an undergraduate, I was taking a physics class, and I wanted to write a paper on how a bicycle stays erect, or how a bicycle is stabilized by wheels. And it turns out it's because of angular momentum. I never wrote the paper, but I remember that being an issue. All right, so we've figured out that electrons have a wave nature, and it can be demonstrated experimentally. It was done so also in the 1900s. They showed that the electrons traveling through a regular atomic pattern in a crystal produced an interference pattern. Right, this is sort of the heart of X-ray crystallography. And the interference pattern is strikingly similar to interference patterns for light. Funny enough, and it's sort of like the water that I showed you in a previous picture. You know what? I'm going to move past this and simply go to the end of this. Thus, it appears that while electrons are small, localized particles, their motion does not follow the equations of classical mechanics. They are not like little balls following. I'm sorry for my voice, and I'm really having a hard time talking today. Electrons, they are not little spheres that follow a classical mechanical trajectory. Instead, some type of wave equation governs a probability distribution for electrons' motion. Thus, the wave-particle duality first observed with photons is actually a fundamental behavior intrinsic to all quantum particles. Actually, it's intrinsic to all particles. We only see it with small particles.